Welcome, everyone. I am very honored to be the first speaker of this great conference. So my name is Ksenia Peguero, and I am a senior research engineer at Synopsys. I've been doing software security, application security for over 10 years now. I used to be a consultant for about 7 years, and then I switched into just research. And on top of everything else, I'm also working on my PhD for George Washington University. And this work that I'm presenting today is actually part of my academic research. So not so much, well, partially part of my job. I'm combining everything, but yeah, that's going to be part of my thesis, hopefully very soon. I'm also a mother and expecting another child any moment now. So it is very, very close. I'm very happy to be here live today. And in non-pandemic times, I like to do things like ballroom dancing and diving, and maybe this will happen again, I don't know, a year from now or something like that. So I also tweet about security at Ksenia Peguero. So I want to start today to talk about Electron.js security. And I want to start with an example of a remote code execution that was reported a few months ago in October of this year by Masato Kinagawa. And that was a remote code execution in the Discord app, Discord desktop app. So everybody who's gaming, who's using Discord for just like chatting with friends, may be very familiar. So if you have a desktop version of Discord, not your mobile version, then it is written in Electron. And what Kinagawa was able to do is basically create a link that an attacker sends to you as a user. So you're chatting with a bunch of people. You don't know who they are oftentimes in gaming. Somebody sends you a link with a video. The Discord app loads the video, just like many other Electron apps. So a lot of chats, like for example, Slack is also written in Electron, right? Like if somebody sends you a YouTube link, you don't even click on it, it loads automatically, and then you can click and play the video within the chat. And then once this video is executed, you basically it executes a remote code execution and starts an arbitrary program on your machine. So from the attack perspective, this is super slick and doesn't take much from the user at all. So let's look at the example here. Here we go. So here's the video that Kinagawa recorded. So basically, yep, you have the screen. Somebody sends you a link. The user clicks start playing. The video starts playing. And then suddenly another application is executed. Like in this case, it's a calculator, right? So pretty scary. And what he did here is he combined a bunch of different small vulnerabilities in the Electron app. And as we go through this presentation, I'm going to talk about all the different security controls that this code execution circumvented and how he kind of linked to them all together to get the navigation, to get the remote code execution. So there was the context isolation, NXSS, and navigation restriction bypass. But first, let's talk about Electron a little bit. So if somebody is not familiar with Electron.js, it's a platform, a JavaScript platform for writing desktop applications. And there are a lot of applications that are using it. So if you are a JavaScript developer and you're using an IDE, there is a very high chance you're using one of these two, like Visual Studio or Atom. They're written in Electron. Project management tools like Flow are written in Electron. A lot of tools for design, games, social networking clients, again, desktop clients specifically, right? There's your WhatsApp, Skype, Discord, etc. And a lot of web apps also have their desktop clients, and the desktop client is oftentimes written in Electron. So why Electron? Why is it so popular? Well, it's an open source framework. And it's maintained by GitHub, so it is pretty, has a very good backing, so it makes it very popular for developers to pick it up. And what it does, it runs two main components. So it runs the Node.js and the backend, and runs Chromium browser for the front end. So it's basically a little server-side, client-side application that's running right on your computer. And both of the server-side and client-side parts are written in JavaScript. So both Node.js and Chromium need something to execute JavaScript. So they're using the V8 engine. And that is great. So they're sharing the same engine, but it also introduces some problems because they need to make sure the versions correspond more or less. Sometimes when Node.js, for example, gets updated and it needs a newer V8 engine, but Chrome hasn't merged to the newer engine yet, then the developers of the Electron have to make some decisions and maybe use an older version of V8. And if the newer version fixed a security vulnerability, that means Electron may be still running the older, more vulnerable version. So there are always these issues when you combine different technologies together. What are the pros of Electron? The development is fast because developers are familiar with JavaScript. Everybody who has written a front end, you can reuse the front end components from your website. You can use any framework like Node.js, like React or Vue or Angular. So all of that can still be used for Electron. Sometimes some of the server-side code can be reused as well for a web app and an Electron app. Some libraries can be shared. Of course, with Node.js, a lot of Node libraries can be reused, and there's a ton of them. So that's all great code reuse. And it is cross-platform, right? Everywhere we can run V8 on any platform. That means Electron app will run on any system. The problems with it is that, as I mentioned before, the version support sometimes is, some versions are behind on the latest version of Chromium or the latest version of V8. And then there are also performance issues, some high memory consumption, but they've been working on the performance specifically, so it's still pretty popular. How do all of these components interact in an Electron app? When we start an Electron app, what happens is, so we have operating system, we have Node.js running on top of it, and we have a native UI. You have your window that you can close, minimize, etc. So then, on top of Node.js, we have two large components. There's always the main process, and then there's a renderer process or multiple renderer processes, depending on how many windows of pages in those windows are rendered. Because basically, the main process is your backend, and then the renderer processes are your front ends. So each of these components are written in JavaScript. They can interact in two different ways. So the main common way of interaction is IPC. In this case, there are specific modules. For the main, there's the IPC main component, and then for the renderer, there's IPC renderer component. It's an event-based system. So one component is listening for the events, the other component sends events. Very straightforward. So here I have the code. For example, the main component has the IPC main, and it listens for an asynchronous message event. The renderer, the client side, sends the event with some string as an argument, and on receive, the main sends another event, asynchronous reply, etc., etc. So pretty straightforward. However, there is another way to communicate, and there is the app class or app API group, as they call it. So usually the app component is only available in the main, and then because it has a lot of very sensitive functions. However, the renderer sometimes can also use a remote component of Electron, and then through the remote call the components that should only be available for the main. So that part sounds, from security perspective, it sounds like we are starting to cross some trust boundaries here. And what happens is, if we trust the renderer if the renderer is only running the code that me, a developer, wrote, and it doesn't have any untrusted code, then yes, maybe we can let it use the app component and have access to other types of events, to other types of functionality. However, if there is a cross-site scripting in the renderer, or if renderer is loading a third-party component from the internet, from somewhere, that's where it starts to become dicey. So in my previous work, in my previous research for other JavaScript frameworks, kind of shifting gears a little bit here, I looked at the places where vulnerabilities can be mitigated in relation to the framework. So if we think about an application, and application has a vulnerability, this is kind of level 1, there is no mitigation in place, this is our baseline. The mitigation is usually some sort of security control, for example, a sanitization function, or like an encryption function, or something else, right? So that control can be placed at a different place in the application if the application uses a framework, from the framework perspective. So it can be some custom code written by the developer. The developer writes their own sanitization function, their own authorization function, or their own, random number generation function, which of course we don't recommend at all. Or this is level 1, so custom function. At level 2, we can be using an external library. So kind of same thing, it's a custom function, but written by another developer. A little bit more trusted because, hopefully this library is popular, used by community, more vetted. The next level is level 3, framework plugin. So if we are using a framework, maybe there is a plugin that does that for us. So for example, if we look at Happy.js framework, it has a bunch of different plugins that you can use. If we look at Express, it has a bunch of different open source plugins that integrate very, very tightly with the framework. And you just call the plugin, enable it set to true, maybe set a couple configurations, and it runs. The next level is level 4, where this mitigation is built into the framework. So we don't need to add some sort of third-party plugin. The mitigation is already part of the framework. And again, there are a lot of frameworks that have a lot of security built into them. So if you look at Sails in JavaScript, if you look at Django, for example, in Python, there are a lot of configurations that you can set and automatically enable. So this is great. That kind of lets developer think even less about security. And then level 5 is when the mitigation control is built into the architecture. So it could be into the language itself or into the platform itself. An example of that would be memory management in Java. So we all know that in Java applications, there are no buffer overflows. And that is because JVM takes care of the memory management. So that's awesome. That's really good. And my hypothesis for the research is that the closer the mitigation is to level 5, to the framework, or even maybe to architecture, the better, right? The less security issues there will be in the application. So for Electron applications, what I did is, I took that same framework and decided to see, okay, what are the common vulnerabilities in the Electron applications? And if we want to mitigate them, where are the mitigations? Where can we place the mitigations for these vulnerabilities? So what I did is I took 141 open source applications from GitHub, from the awesome Electron library. And it's a pretty wide variety of applications. So there are like Markdown editors, Messenger apps, like the Discord and Signal, database clients and password generators, and like all kinds of different apps. And I took an open source tool that's called Electronegativity, developed by LocoMocoSec, that scans Electron applications and reports a huge CSV file with a bunch of findings. And then I manually analyzed these results. And I'll talk about results a little bit later. And out of for these 140 something applications, most of the vulnerabilities reported fell into the 17 categories, and then out of those 17 categories, 8 of them, about half of them, were more commonly, there were more occurrences of that. So I decided to focus on those first 8 categories. So the first kind of top half. The total, I had 1,180 total defects reported by electronegativity. Out of them, about 460 findings were more like best practices. So they weren't leading to actual vulnerabilities. So there were things like, oh, you're using an older version of Electron. So like, okay, well, good information, but not really exploitable right away. So I discarded those because I was interested in things that can actually be exploited right away. And then out of the 1,200 that were left, I did manual analysis of all of them, manual review, and found 218 of them were true positives and about 1,000 were false positives. So, the quality of electronegativity is, an open source tool, but it has some limitations, obviously. And the problems are that it is an AST, it does AST-based analysis only. So it only looks at the abstract syntax tree. It doesn't look at the data flow. It doesn't look at the data propagation. So it doesn't track the data from sources to sinks. And that leads to a lot of false positives and false negatives. So for example, in this code here, we create a browser window, which is a very common functionality in Electron. That's how we create a renderer process, right? The browser window that will then render the client-side code for an Electron app. And it has some some settings. And so if we set a sandbox setting to a variable that we defined earlier and said, sandbox 1 set to true, electronegativity actually will not be able to identify and see what the sandbox value is set to because it doesn't do the data propagation. Obviously, it's straightforward to a human to see like, yeah, it's set to true, but it will actually report a finding here because a sandbox is by default set to false. That's the default value of the sandbox. So that's why I had to do the manual analysis. So after I cleared all the results and got kind of the real data, as I said, I identified the 8 types of vulnerabilities and decided to concentrate on those. And going back to my question, I wanted to see where would the mitigation be for each of these vulnerabilities. If we wanted to have more secure code and help developers, where would we place the mitigation? So in this presentation, I'm not going to go about each and single one of them because we don't have enough time, but I'm going to look at 3 that are more interesting. So we're going to start with node integration. And the finding that electronegativity reports is node integration JS check. So what node integration does, and this is a functionality of Electron app that makes Electron apps makes them do what they're good at. And what their strong point is that when you run that client, when you run the client side of the Electron application, it can call Node.js services. It can call server-side code right away, and that's what makes it look like a desktop app. It's so super responsive, right? It can open files. It can listen to your network. That's what a normal desktop application can do, and that's great. That's what makes Electron applications. However, there was a vulnerability, here an example, in 2018 in a Signal messaging app, where, again, it's a messaging app. You're chatting with an attacker, somebody you don't know. They send you a link. The link executes cross-site scripting because the front end is written in React, and it was using the dangerously set inner HTML function, which is vulnerable to XSS because it doesn't do any filtering or escaping of the code. And then that code basically executes a remote code execution. And the reason why this is, like, if that happened in a browser, if you have similar front end loaded in a browser, the browser will not allow to start an app, or in this case, read its password file, because the browser is isolated and it doesn't have access to the file system. But with Node integration enabled, that makes Electron applications able to do things like that, to read files. So how do we protect that? Well, we turn that Node integration off. And unfortunately, in Electron applications, that Node integration feature was enabled by default for many, many, many versions of Electron. So by default, it will be set to true. And then if you wanted to disable it, then a developer had to set web preferences for each browser window and say Node integration equals false, right? And then for the web view component, which is another component that can also render untrusted code, it was off by default, which is great. But it could also enable, if there is a cross-site scripting, an attacker can create their own web view component and then set the Node integration to true as well. But luckily, in Electron version 5, Node integration was finally set to false. So that's great. The next security control. Oh, and so if we look at the mitigation level, right, this is the mitigation of this problem is part of the framework. And especially if you just change the secure default, it is on level 4, right? So it is built-in framework mitigation. The next one is very similar. It's called a sandbox. So when we run the render process, again, if we think about a Chromium browser, if we think about a regular, Chrome browser, each browser has that notion of a sandbox. So the code that is running in the browser is isolated from the operating system. It doesn't have access to Node.js API. It doesn't have access to third-party modules. It is isolated. Well, in Electron, it is not isolated. That sandbox of the Chromium browser was removed. This is like an additional control to the Node integration. And for example, what it does, it disallows the require method. So you cannot call a third-party Node.js require components. And then you cannot call that app class through the remote class of Electron. So all your communication only happens through IPC, so only through the events that were defined previously and the events that the server side is expecting. So it makes the application even more secure. But unfortunately, by default, it was set to false. And again, to enable that in the web preferences, we have to say, sandbox equals true. So it's a mitigation that's built into the framework, but the defaults are not secure, and they're still not secure. And then the third one is context isolation. Again, it deals with protecting the render process from the main process. But in this case, you have the same JavaScript engine running the code on the server side and on the client side. And there is a vulnerability that is specific, a trick that is specific to JavaScript applications, and it's called prototype pollution, where an attacker, anyone can overwrite a built-in prototype function. In this case, for example, we have a preload script, and that is a script that's executed before the renderer process loads the untrusted code, or whatever code that from an external URL. And at that point, it still has access to all the Node.js components. So in this case, in this example, we have a set of safe protocols, HTTP, HTTPS, and we have this check, right? So if we are trying to open a third-party link, if the protocol is in the set of these safe protocols, then allowed to open external link. However, we rely here on this index of function. So, for example, if we send a link to file and try to open a calculator, for example, this control should protect us. But if through the prototype pollution, we're able to override the index of function, which is a common function for all the arrays. So it's a function on the JavaScript prototype. and say, oh, this function always returns 1, then no matter what is the protocol of the link, if it's mail to or file, it will always return 1, which will be not equal to -1, and that will execute any link. And that is, again, because we have the same JavaScript engine, the same JavaScript environment, which is not isolated for the render process or for the server-side code that has access to other functions. So the context isolation, again, even if node integration is disabled and a renderer component cannot load the Node.js function directly, it can override the prototype functions. And this trick a little bit, it's a little bit more advanced, because then the developer or the attacker needs to guess what kind of built-in functions are used by the server side. But of course, if the application is open source, they can look at it. Even if it's not open source, it's a JavaScript application. It's pretty straightforward to open up the desktop the Electron applications once you load it, and you can see all the JavaScript source code there, right? So it's pretty straightforward to find that function and override it, and then just wait for the server side to call it in the right place. To enable context isolation, again, it's a simple setting. In the browser window, you just say context isolation equals true, or in a web view, once you create it, you add the context isolation as one of the web preferences to that. When the node integration setting was changed in Electron version 5, context isolation change was also proposed, but that never happened. Now it's still proposed for Electron 12, so hopefully it will be fixed by then. We don't know. So if we go back to the exploit on the Discord app, right? What actually happened there? Well, the node integration was not enabled, which is good. So that link could not call the calculator directly, right? But what was not enabled was the context isolation. And so what Kinugawa was able to do is, through prototype pollution, to override the test function for the regex and the join function for the array. And then they used the iframe embeds function with an XSS in it. So as I said, the chat would load a video and then execute it within an iframe embeds object. And the Discord app actually had a content security policy, so it would only allow videos from certain sites. Well, for example, Kinugawa had to find one of those trusted sites that had an XSS in it. One of them was YouTube. YouTube did not have an XSS in it, but it found some other site, and as you saw earlier in the video, was just like a 3D modeling site that would provide 3D models and have little videos built of them. So he was able to create that 3D model that also contained a cross-site scripting in it. And then when that cross-site scripting is running, because it's running inside an iframe, we would expect that XSS only executes in an iframe and therefore cannot have access to the top-level document. So to make it actually execute code on the user's machine, it has to be running at the top-level context. However, there was also a bug, basically in Electron, that allowed that navigation restriction bypass, because the event that was generated, that should be generated every time there is a new window opened, for some reason wasn't generated when the origin of the iframe was different from the origin of the main document. So that was the bug that Kinugawa reported to Discord as well, or to Electron, and that was addressed fairly quickly. How could we stop this attack as a developer, right? So one thing is obviously enable context isolation. So kind of one thing was in the control of developer. Another thing was a bug in Electron that was not in the control of developer, and that's something that Electron had to fix. But even if the context isolation was enabled by default, this vulnerability and attack would not be possible. Well, and as I looked at all the different vulnerability types, the 8 that I discovered that were more common, most of them could be mitigated at level 4, and 3 of them could be simply mitigated by just changing the default to a secure value. So very straightforward fix. Unfortunately, it takes a very long time to fix those things. As we've seen with like node integration that has been fixed, that's good. But other ones like context isolation or sandbox have not been changed before. And I understand, I mean, there are dependencies to make that change. That will be a breaking change, and that's why it takes a long time to come to this decision. But, we want to write secure code. So what I did as part of my research is I created a Visual Studio Code plugin, and I called it Electrolynd, that basically helps developers to identify those locations in the code earlier in the development lifecycle, so that we don't have to wait until the framework fixes all the secure defaults or fixes the underlying issues. But maybe if we just nudge the developer and say, hey, why don't you set this setting to this value? Why don't you add a sanitization routine here and check the protocol, for example, of a function that you're trying to open, and it's it's coming from an untrusted user. Hopefully, that will make the applications more secure. So what Electrolynd does, it uses electronegativity underneath it, so the open source tool electronegativity, and then it highlights the vulnerabilities straight in the code, as a lot of plugins, obviously, IDE plugins do. It highlights the location. It lists all the findings there. It also, it shows the description from Electrolynd, but in addition to that, it also shows the mitigation advice. So very contextual mitigation advice. So in this case, for example, we're creating a browser window. It's you save the file, Electrolynd runs automatically and says, hey, there is a context isolation JS check vulnerability here. Why don't you set the context isolation to true in the web preferences, so that you can avoid prototype pollutions. It also adds a little bit of information about what will change, what attack you will protect your code from. And the plugin is available on GitHub. Please follow the link, check it out, download it, send me your recommendations, tell me which you're thinking, and if you want to contribute, that's great. And with that, we can go into Q&A. All right, I do not. How can we go back into the discussion? Okay. So I stopped sharing. Yes, guys, you can still hear me. So if there are any questions in the chat, yes, I will be happy to answer them.
Hey, so sorry about that. We were actually trying to troubleshoot the audio of the next speaker, so I had to jump away. Thankfully, the volunteers helped let me know that we're back. Thank you. I caught all but the last 6 minutes, I'd say, and up to that point, very informative. Obviously, Electron is something. Since I work at GitHub, I'm very familiar with the security flaws and the submissions we've gotten over the bounty with Electron. So yeah, thank you so much for your time. We greatly appreciate it. I'm going to check our feed for any questions. Brian or Abdullah, did you have anything you wanted to add here?
No, I'm checking the feed. I don't think I see any questions. Audience, once again, if you do have questions, you can just add them directly to the chat there on the right of the YouTube live feed.
A lot of people just saying hi and thank you and yeah, positive things, no questions. So
I think, yeah, Stefan had a question.
Let me add Stefan to this.
Hey, Ksenia, that was really great. Thank you very much for that. We deal a lot with wallets and things like this in Electron, and I think there's you laid out all of the communication protocols very well, and it's very difficult for devs to get access to these sorts of things. And I apologize, we were testing an audio in another one if you covered this, but for the sorts of things that devs should be doing, I usually throw them at like DoinSec's guide. I throw them at some of the things that Synopsys has put together, like that sort of thing. And again, I apologize if I just missed this, but are there like some ground truths that devs should be following? Because it seems like Electron is usually just a Wild West that people sort of, assume is secure because of course it is, and it really isn't.
Yeah. So every time, like my main point is that every time you're loading a render process, unless it is rendering just your built-in, index.html file that doesn't load anything else from the intranet, then you can enable your node integration, context isolation, not enable context isolation or not enable sandbox. But kind of my main suggestion to the Electron developers, to the Electron framework maintainers, is that we should turn on the secure defaults. And I would start with a render process that cannot do anything except for rendering the UI, basically. And then when you say, oh, that doesn't work for my app because I want the users to open a file, etc., then you go back to your kind of security dashboard and you say, okay, yes, this one window should be able to access the operating system. And you can do two things. You can set the node integration to true and say, okay, now you can do anything. You can load files, you can listen to the network, you can do whatever. Or again, you think, what are the actual functions that one window needs to do? It needs to open a file. Well, how about we just write one function in the preload script that allows to open a file? And then that renderer can call that one function. And then, of course, you check the arguments, right? What file it's opening, etc. But you don't allow everything else. So it's, like, giving the access to the things that window just needs, and that's it.
Mm-hmm, mm-hmm. And also, too, it's interesting because so much of the Node.js ecosystem is broken. There's a lot, not because of things that Node.js is doing, but because people specifically target things in Node.js. There's quite a few, like crypto key stealing library attacks that we've seen and whatnot there. But what sorts of things? Obviously, you work for Synopsys. They have solutions to these sorts of things. But what, as an academic, what do you see as the where that space is heading towards? Like, what sorts of things can devs do for that? Because that's also the other problem too, besides the lockdown issues that they have.
Yeah, and that's why I created that free open source plugin for Visual Studio, beautiful. Right? So that's exactly why, right? And what the plugin does, it runs electronegativity, so the DynSec guys, tool, but it also, instead of generating the CSV file at the end that you then have to manually analyze, and as I showed in the presentation earlier, a huge percentage were false positives, but that's fine. So what my tool does is it only looks at those top 8 that I identified that usually are true positives, highlights them in the IDE, in the Visual Studio Code, and provides the advice right there where the developer is writing the code at the line of code. And of course, not all advice is going to be true, right? Because the developers may say, "Oh no, we know we are loading third-party content. We are trusting it. We're loading it from our trusted server. Like that's what it's supposed to do. And so your suggestion is a false positive suggestion." And that's okay. But if it's not, then that's where you can fix your code, right? Early, and it's free, open on GitHub. So yeah.
No, that's great. And then also too, just because you work in the space, one of the things that we often run into is we like at Trail of Bits, we do lots with like fuzzers, property testing, symbolic execution, that sort of thing. And there's a lot of tools in the Node or in the JavaScript space to do some of these things, but they're sort of nascent, or they were like a research paper and things like that. Where do you see the sort of future for Node security going? Since I think there's abortive attempts to try some of these sorts of things, and then they sort of stop. So like, as someone who studies it, what do you see the future is heading towards?
So my hope is that the future is going towards fixing the issues, right? A lot of the symbolic execution, like again, research in symbolic execution, research in Node.js security is targeted towards finding the bugs, finding the issues. If we look at research on JavaScript frameworks, it's all about performance and quality issues, right? There's not much research in terms of security of the frameworks. And I hope that academia will kind of catch up to the industry, right? You know, in the industry, we've been talking a lot about, okay, we were finding bugs. Now it's time to build the security in to fix the bug, to provide the solutions for fixing the issues, right? So hopefully academia will turn into that direction. At least that's what I'm trying to do in my research, and provide the tools that either are native to the developers and they help to fix the things, or that are fixing the frameworks, or that provide something in the IDEs, or provide some sort of wrappers to the code that also fix the things earlier in the pipeline. So.
Yeah, it's amazing how exposing something in Visual Studio for a dev will get their attention when the whole of CI/CD pipelines and all the things we've been doing for years have not done that. But making it accessible and making it upfront is really great. No, but I did want to pick your brains on these sorts of things, because this is something we run into all the time, and you've done the deeper work here. So this was great. Thank you very much.
Thank you. Thank you very much. Well, it was a pleasure.
There is one statement here. Let me pop it up on the screen. So is it safe to say if a Electron app has access to files, then safe to say Node integration is true, like attaching images if Messenger app, etc.?
Yes. So kind of yes and no. So Electron can have multiple render processes, right? And so if the process, if that happens in two different processes, may have one process that allows you to attach a file, and so read something from your operating system, and then the chat, for example, is actually running in another process. Then the processes are isolated, and then it depends how they communicate, right? What they can kind of how the server side is written, right, in terms of communication. But yeah, it depends. It depends how the server side is written, basically. Because if you think about any IDE plugin, like IDE in general, like Visual Studio Code obviously has access to your file systems, or Atom obviously has access to your file system. If you think about a Slack, right, obviously has access to your file system, because you can upload as a user, you can download, etc. But basically, if there are controls built into what do you do with the links that are sent from a third party versus what do you do when you open the dialog and say, hey, select this file and send it to my friend? Yeah, that's where the trust boundary lays.
Awesome. Well, I think that, I think that was the last question. So yeah, just once again, thank you so much for your time and for your putting out this valuable information, since so many things are built on top of Electron, and we all have to be from a consultant perspective to a blue teamer perspective, it doesn't matter. We should all be focused on the security of apps built on Electron. So once again, thank you so much for your time.
Thank you for having me.
All right. Thank you.